Okay, Assalamualaikum and good morning. So we'll continue with the lectures for this week. So let me see. We have gone through idea of vector operators. Essentially, what we did was to look at how vectors transform in classical sense, and then one actually uses a well-known principle that your quantum mechanical quantities that you get in quantum theory will behave like the classical case whenever you take the expectation value. So essentially, this is the equation that we had earlier. So this equation is coming from the analogy with the classical equation over here. Okay, so in other words, now we are able to precisely state how vector operators actually behave in response to the classical equation that we had, say, in classical mechanics. And that principle is actually called Ehrenfest principle. I'm not sure it has been taught anywhere. Sometimes even in my own first course, I tend to skip some of this idea, but you can actually try to read this up. Let me just look at, I open up the Wikipedia here. So you have this idea of Ehrenfest theorem. Okay, this is essentially one of the guiding principles to build quantum theory in a way. Besides another thing that people use are what is called a quantization procedure, but we also have Ehrenfest theorems to somehow guide how to do a possible quantum theory. So in other words, all your classical equations stays. For example, in this particular case, you have what we call F equals to ma here, for example. Okay? And that F equals to ma actually comes in the context of quantum mechanics through Ehrenfest theorem. Okay? So generally we have this. I think most probably in my first course, I tend to just say this we call equation without mentioning that this is actually the Ehrenfest theorem. There is another one which without the expectation value, which is called Heisenberg equation of motion. So that requires the Heisenberg picture of quantum theory. Right. So let's go back to this. So our next point is essentially, so this is essentially looking at a specific case where your rotation operator is actually coming from, say, the z axis, and then you'll find you get these equations involving commutators, okay, and that those commutators, so get equations of commutators involving commutators and commutators form this is for those who are involved in quantization. Commutators involves the idea of what should I say Lie groups, okay, Lie algebras, okay, and then how you have a particular Lie algebra actually refers to a kind of a transformation inside your quantum theory. So, so that is basically what this part is actually doing. So essentially now one have any set of operators, and you can think of the set of operators just being components, and these components must behave accordingly through the commutator with the angular momentum, for example. Okay. So one of the things that we have actually seen over here is probably the position operator with angular momenta. Okay, so the position operator normally we write it with a vector notation. So that is a set of three operators, and set what I call sometimes what happens in this particular case, you might consider even a tensor product if you have separability of the Schrodinger equation. So it depends on the physical system. Sometimes you can actually separate these variables. In other words, what happens in this particular case, then if it's separable, then you can look at individual components as if they are actually being the tensor product within the say X component of position, Hilbert space, and so on and so forth. Okay, so similarly with your momenta, okay, so you can think of it as having three different operators here, and these operators must obey this particular vector form of the algebra here. Okay, so I think that's where we have finished at the last lecture. So let us now try to generalize this idea. You know that in mathematical physics, or no, in physical theories, the idea of vectors can be essentially generalized, okay, to tensors. In fact, vectors are considered as tensors of rank 1. So in other words, over here, tensors can be of a higher rank, for example. So I hope you have come across tensors before. I think it's dealt with in the course of mathematical physics. Have you seen tensors before?
Yes, doctor.
Okay, great. So that means I don't have to say too much about that. So where are we here? So there, this is not quite correct, but an n index tensor, for example, so that means instead of a single index that refers to a component of the vector here, you can have an object, say T, which has n index, and this is really, to be precise, this is actually what we call a Cartesian tensor of rank n. Okay, so an easy way of thinking about what you call this tensor would be just a tensor product of, say, vector operators. So V and W is a vector operator. So here is tensor product between V and W. Okay, and that V tensor product W will be a Cartesian tensor of rank 2. Okay, and a vector itself, in this particular case here, I'm just writing down the component instead of the whole vector. The vector Vi is essentially the special case of the Cartesian tensor of rank 1. One might ask, what is tensor of rank 0? There is such a thing, and it's called scalars. Okay? So they are just pure numbers, and they don't essentially they don't change under change of basis. Okay, so the idea now is we already have the idea that the vectors may change basis, and they will have different components. Okay, so same applies to tensors in general. So when you change basis, usually in the idea of the classical case will be the basis of the vector space. But in this case, now you actually have your basis to be considered is the basis of a Hilbert space. So the thing is a bit more complicated than what happens in classical mechanics. Okay, so let's just recall in the case of the classical case. Okay, remember that we build our equations in quantum theory based on what we have actually known in classical theory. So in this particular case, a tensor of rank n, a Cartesian tensor of rank n, should change under change of basis from this transformation law. So essentially for each of these index, I1 to In, there will be a rotation matrix multiplying it. So here, in other words, over here, I'm not sure whether it's clear to you, it's I1, I1 dash, and I1 dash is being summed with this I1 dash on the object T. Okay. Similarly, for this index I2 dash, this is multiplied with this rotation matrix Ri2, I2 dash here, contracted with this index. And you do this for all of the indices until the last one, which is In dash. So in other words, over here, if this is actually n index, n indices, so over here there will be n rotation matrices. Okay, so here's the simple example like I essentially mentioned earlier, using a different symbol, of course. Here one can, for example, take two vectors and then pick the tensor product. Okay, so you get a general. So another thing, when we do the notation with respect to the components, a general case would have all these index to be different. Okay, for example, here is UIVJ, and this UIVJ is a tensor rank 2, which whose index is IJ, corresponding to this IJ over here. Okay, so this is tensor product of two vectors, which is a tensor of rank 2, and it should behave under change of basis through the multiplication of two rotation matrices. Okay, so this is classically. I hope it's the next one should be the. Oh, okay, not yet. So now this is where it gets a little bit more complicated, because sometimes what actually happens is one can reduce a particular tensor to several different parts, which is called an irreducible tensor with respect to the rotations. Okay, so maybe I just show you what it is over here. So you can look over here. I can think of this tensor product between UI and Vj, okay, having several different parts corresponding to different behaviors of the tensor of the tensor product according to rotations. Okay, so here's one where I consider when I and j, those components will be 0 in this part, of course. Okay, it will be 0 when I is not equals to j. So this corresponds to essentially what we call the dot product. Okay, and that's a the factor 1/3 is normally it's kind of normalization thing, but no, it corresponds also what happens onto the other parts. So here's the scalar part, and then here's the vector part. And if you can actually see, the vector part involves some kind of an anti-symmetric combination. Okay, so if you want to think about what actually happens over here, if you have a dot product here, then here essentially is like a cross product. Okay, so in other words, this part will behave like a scalar, this part will behave like a vector, and then the rest of it, okay, which is not included in these two parts, will appear here as the so-called irreducible tensor of rank 2. Okay, so you can see over here, if you just simply add up all these quantities here, you get back to UIVJ. It's just a kind of special arrangement between the product of the two components of U and V. Okay, so here, if you can actually see here, there's a symmetric part. Okay, sort of differentiating with the anti-symmetric part here. So this symmetric part, together with the U dot V, the U dot V is also symmetric. You can think about it. Okay, U dot V is V dot U. So it subtracts this because the U dot V sort of relates to the properties of a trace. So in other words, here is telling you that this tensor of rank 2 over here is symmetric, but it's traceless. Okay. So now how do we actually get the idea of how to do this? This is where I think one should go to something with respect to most of the time we're going to actually understand components of tensors with respect to rotational transformation. Okay, so that's where one considers, for example, how angular momenta will generate these rotations, and then how this will actually determine what kind of tensors decomposition that you can actually have here. Okay. What is this? Okay, this is just reiterating what I'm saying earlier. Okay, but an important thing for you to know is the number of common components for each of these objects, and it should correspond to the number of independent components that you find in this tensor product here. So here, for example, a scalar should have only one component. Okay, and then here it should be 3 because you have a vector. And then if you really count a symmetric tensor of rank 2, which is just a matrix, you can think of a matrix, okay, and it's symmetric. So in other words, let's say, what should I label here? Let's say S11, S12, S13, and because of the symmetry here is S12 again, S22, S23, S13, S23, S33. So this is a symmetric matrix, but you also have this condition that S11 plus S22 plus S33, S33, sorry, should be equal to 0. Okay, so in other words, this is the trace and it has 0 trace. Okay, so if you look at the number of independent components over here, you see that, okay, this off diagonal one, there's 3 of them, and then there's another 3 of them on the diagonal, but you have a constraint, so effectively you only have 2 there. So essentially 3 here plus 2 on the diagonal, that gives you 5 different independent components in this symmetric traceless tensor rank 2. So if we just add up, here's 1, here's 3, here's 5. So how many independent components are there? If you add all the components here, you get 9. Okay. Oh, I have this responding to that. Never mind. So here is the, here you remember is a tensor product between the vectors. You will find that if you consider all possible pairs of I and j, there will be 9 of them. But you can actually decompose these 9 independent what you call components into this irreducible components according to a rotation, because each of them will behave differently in a rotation. Okay, so essentially this comes to this kind of equation that you often find this also in group theory when you do tensoring between one representation to another representation. Okay, so but never mind. That's I don't want to elaborate that thing over here. So you might want to see this probably in the context of particle physics, for example. Okay. All right. What's the other thing that should be considered here? Again, as I mentioned, how you decompose this is actually is relative to some kind of transformation of the basis, and that transformation of basis actually refers to the rotations. Okay, so if you actually look at what this 135 numbers is supposed to be, it's like the number of components that you have for orbital angular momentum. That's when L equals 0, that's only M equals 0. So you have the 0, 0 states. Okay, and for L equals to 1, then you have a set of 3 different states: 1, 1, 1, 0, and 1 minus 1. Okay, so in other words, there are 3 different here I talk about multiplicities rather, so that means you will have the same j value but different m values. And then for L equals to 2, then you know that you have 5, okay, which is 2, 2, 1, 2, 0, 2 minus 1, and 2 minus 2. Okay, so that form, sometimes you call this as a multiplet. So this is a singlet, this is a triplet, and this is a quintuplet. Okay, so and because it refers to the components of the orbital angular momentum, sometimes we call this as the reduction of the Cartesian tensor. The Cartesian tensor refers to your x, y, z as your components. Okay, but now you refer it to the way it behaves under rotations. So this is sometimes called the irreducible spherical tensors. Okay, so that will point to the fact that you need to know how a particular operator later on or a state will behave according to this rotational behavior. Okay. So one of the things that we have actually learned, we have learned about spherical harmonics. Okay, and your spherical harmonics depend on this angular variables theta and phi, and theta and phi actually characterize a particular direction. So I can rewrite, for example, YLM theta phi to be equivalent to this YLM as a function of n, where n would be no, characterized by those angles. Okay, so we will start thinking of doing this I think in the next few pages. And okay, so in other words, once you have that, then there's no restriction for you to replace that n by another vector v. So one could actually replace that by a vector v in general, and somehow this will be related to, as I said earlier, all these multiplicities coming from how it behaves in a rotation will relate to the Cartesian tensor in some sense. Okay, here is actually a spherical tensor. So this spherical tensor, okay, of rank k is defined with these possible components, which behaves like a spherical harmonic. Okay, so in other words, this is already a spherical tensor. So the one with the Cartesian tensor, then probably you want to think of a tensor product. So in this case, if it's rank k, then we might want to consider tensor product of k vectors that give a Cartesian tensor rank k, but it doesn't have to be that. But no, in other words, you can take, for example, two Cartesian tensor of say k plus n and then k minus n. When you add those together, then you get rank k. Okay, so right. Let me see what's next. Sorry about this. I was doing something else. Was preparing for the next set of lectures, which I still don't have any notes at this juncture. Right. So one can start to look at how our spherical harmonics sort of relate to your, say, Euclidean parts or the Cartesian part, sorry. So in this particular case, you have seen, for example, your spherical harmonics given in terms of theta, for instance. Okay, so y10 is given by this function square root 3 over 4 pi cos theta. But now this cos theta, how can you relate this with your Cartesian components? You know that, okay, if you remember how we do spherical polar coordinates, your z is essentially r cos theta, and then x is r sine theta cos phi, y is r sine theta sine phi. Okay, so you start looking at the spherical harmonics themselves, and then how the spherical harmonics relate to the Cartesian components will actually tell us how to do this tensor decomposition in some way. Okay, so here is if you think about this, let me check properly. This is supposed to be sort of flip the indices here. So let me check how I define above. Yeah, so you can see here the rank is here, but your k actually appears down here, and q is here, but your q appears on top there. So pretty confusing. I mean, but no, just bear with this kind of notation. This is found inside your Sakurai book. Okay. So over here, this is your L, right? And this is your M. And that should relate to the case of your spherical tensor with rank 1 here. and component 0. Okay, the component 0 correspond to the n. So how I can relate to this to the component of a vector, because this is rank 1, so I can rewrite this as Vz. Okay, and this is coming from here. Here, why you have not just z, because remember that this is coming from taking v here as a unit vector n. So then you actually, that unit vector has to be normalized, so it divides by r there. But for a general vector v, then it would be corresponding to the z component only. Okay, so this is how we start to generalize our idea how to relate a spherical tensor to a Cartesian tensor. Okay. And then next we have the plus or minus 1 of the L equals to 1 spherical harmonics. Okay. Usually it gives in terms of, I can remember, exponential of the phi case, and then there will be some cos and sine. Let me just check. We'll go to the Wikipedia page. Excuse me. Throat's getting dry. So just to remind us what the spherical harmonics looks like. So let's go down here. There must be some kind of table that tells us what the spherical harmonics are. Oops, gone too far. This is the general formula, and again, I want just a standard table that shows what it is. Let me see. Well, it's not up here, so it has to be down here somewhere. Oh, never mind. I mean, you can look it up. Okay. Doesn't have. Okay. I can certainly look up at my notes, but I don't want to do that. So you just find out what why 1 plus or minus 1 in terms of the angles, and then see how it corresponds to your x and y. So here is the it's already given here. Okay, so you can imagine that this is this thing without the r, of course. Here you get your cos sine theta cos phi plus or minus sine theta sine phi. Okay, and then you should be able to correspond this to the case of the ordinary spherical harmonics. Okay, so now what we wanted to do is to think of your y1 plus or minus 1 to be a general spherical tensor here of rank 1, okay, with plus or minus 1 components. Okay, and how does it relate to this Cartesian decomposition thing is now given in terms of this Vx and Vy. So I hope you can now see the correspondence now between the spherical harmonics and the spherical tensor here. Okay. So one can actually do this for higher ranks. This is just for the case of rank 1, so you can go to rank 2, so it gets more complicated along the way. Okay, so here's a spherical tensor corresponding to the spherical harmonics, okay, rank 2, okay, and then you have your components which relates to the components of this vector v here. Okay. Why are we doing all this? Is we want to come to the point of how states are going to behave under rotations, okay, the quantum states. So remember, our quantum states can change its basis under the rotation what I call operators. Okay? So rotation operators, what does it do? It really is just to change the basis. Okay, this is a unitary matrix here, and one could relate this kind of structure with the spherical harmonics by just looking at the position representation. So here's an angular momentum state, Lm, and then your n here will sort of determines the direction in terms of theta and phi. And then you can see now, okay, if I can do with n dash over here, then I can simply use the general vector v in order for me to get a general spherical tensor. Okay, so I have that, and of course you also have this rotation operator that you need to worry about. Okay, and the rotation operators can be expanded in terms of its components. Okay, so that is another matter that one has to worry about, and this actually correspond to how you know how the rotation matrix actually acts on this quantum state Ln. Okay, so what it does over here physically is actually start to permute all these different components of M, okay, but preserving the total angular momentum L. Okay. So I can now start to do this. Okay, once I know how it rotates the angular momentum states, then I can start to expand your spherical harmonics in this particular way, and that sort of relates what we want to do in terms of the spherical tensors. Okay. So now instead of n dash, now I can replace this by v. But remember, okay, the other thing that one should also have is the fact that if you think of this as an operator, then the essential transformation is involving d dagger here and multiplying on the left and d multiplying on the right. If you remember, operators behave in this way. So let's have this is from the first course. Sorry. So this will change in that way, but for the states, okay, this will change in this way. Okay, so you have to remember all this basic stuff. So now, if I want to consider how a spherical tensor behave under rotation, okay, then I will actually have analogous equation for the ones above for the spherical tensors. Okay, so again, the correspondence you can actually see d dagger r here is okay, here is rank L, but I'm replacing this with rank K. Components Q will relate with the components M here, and then essentially remember the M replaced by Q, so you have D Q Q dash, and rank L replaced by K, and then you also have the Y and M, which now replaced by the tensor. Okay. Okay. So now these are in terms, remember that the rotation matrix that we put there are essentially unitary matrices, and unitary matrices are the ones that change basis. So if you really want to see how tensors behave according to the generators, okay, which is in this case that will be the generator of the rotation matrix or rotation operators, sorry, then one use the infinitesimal version of this exponential thing. Remember, this exponential thing is essentially the unitary operator. So you just plug into this. Then let me just check. So I'm using the one below. The one below is just sort of taking the inverse. Well, it's just taking the adjoint of this earlier earlier equation. Okay, so here you can see that this. No, actually I'm doing this, right? Yeah, dr is given by that, so I have that exponential thing. Okay, so I get a minus there, and then d dagger will have your plus. Okay. So now what actually happens over here? Here you have operators. Okay, and then over here you have the matrix elements. Okay. So once you start to simplify this particular equation out, okay, and then removing the identity. Oops, what did I do? Removing the identity part, then you get a commutator from this part of the from this left hand side, and then on this part you'll get your just j dot n thing, because your one will be removed from the other left hand side, and you're left with this behavior of this spherical tensor expanded in terms of the matrix elements away. Okay. So if you choose your n to be in a particular direction, usually you consider the z, for example, then j dot n will be jz, and then the commutator between jz and tqk, it will be related to this part on the right hand side. And let me just see, here is jz, remember, let me write it down. So here is supposed to be k q dash, sorry, looking at my cat, what's doing here, jz kq, but kq, remember this is like lm, it's an eigenstate of jz. So in other words, this will give you h bar q kq dash, and this gives you delta q dash. Okay, so in the end you can actually get this particular equation, which tells us about a spherical tensor of rank k with components q, how it commutes, how is the commutator relationship with jz. Okay. You also have to check with the other direction. So here you're putting n in the z direction. You can put your n inside this different directions here. Here's a linear combination here. So why do we do this? Because we want to relate with the step down and step up ladder operator. Okay, so once you do that, then you have j dot n will becomes j plus or minus operator. And how will this commutator relates to the spherical tensor in terms of increasing the q values. The q values, remember, is corresponding to your m, so it will behave in the same manner. So once you have this tells us, okay, you get a spherical tensor operator. Okay, so your tensor operator will behave under rotational transformations in this manner. Okay, so let me see. Yeah, next thing is to look at product of tensors. Okay, so we have seen earlier how we build tensors by taking a tensor product. The one that we have seen example on is essentially just a tensor product of two vectors. You can generalize this if you want to. So in the example that we had the tensor product of two vectors giving you a rank 2 Cartesian tensor. Okay, and this relates with the case of a scalar product between vectors. So you had that, for example. I'm not sure that there are plus or minus. I can remember what we did earlier, but these are just conventions, really. I think the plus or minus has a different sign here, probably because of the I that appears in the plus or minus definition. Let me just check. Yeah, so here you don't have that minus sign. So this will give you a scalar operator, and from the scalar operator you should be able to write down what's the commutator with the angular momentum operators. Okay, here would be the vector operator. And then this will be the, let me just think. Which one is the symmetric one? Yeah, yeah, all symmetric. Yeah, they are all symmetric. Let me think. Let me just scroll down a little bit, see what I'm doing. Above. So this should be the symmetric case. I'm just trying to think of where is the restless part. Maybe I'll get back to that later on. So this is symmetric tensor with the components plus or minus 2, and then again rank 2 tensor here with components plus or minus 1. something I've forgotten about here, but never mind. So tensor rank 2 here, you have this 5 different, yeah, okay, now I can see what's going on. So you have 1, 2 here, 2 here. So essentially these are the 5 components of the symmetric tensor. Sorry about that. I left this thing for some time. So as to see here. Yeah, so your plus and minus 1 component, remember that this only correspond to your ux and uy combination. Okay. So finally we have a theorem essentially telling you how to do the tensor product between two general tensor operators. Okay, so here is a tensor operator of rank K1 and rank K2 with components Q1, Q2 here. Okay, so the idea is that you can form a tensor of rank K, by this tensor product of this X and Z of rank K1 and K2 respectively. And these are essentially like your Clebsch-Gordon coefficient. So now you can actually see what's happening here. Your KQ here is coming, is analogous to your case of your JM in the theory of addition of angular momentum. Your K1, K2 here, this corresponds to your J1, J2, M1, M2. Okay, so in other words, all these spherical tensors just follow simply from the theory of addition of angular momenta. Okay, because remember each tensor operator are behaving in the same way as your spherical harmonics. Okay, so in other words, the way all these spherical tensors behave will follow the addition of angular momenta. Even in the case of your spherical harmonics, you have the same theory, okay, of angular momenta addition. So it also applies in this particular case of the tensor case. Let me see whether I want to do this or not. So this is the proof. Again, okay, shall we take a break and let me just read this particular proof? Shall we? Okay, let's see, 5 minutes. Are you guys back?
Yes, doctor.
Well, okay, so let me continue. I also open up the previous lecture that we had was lecture 4. And if you remember in lecture 4, we talked about the Clebsch-Gordon series. Okay. So this is the Clebsch-Gordon series. So essentially what happens there, one looks at a particular what you call matrix element of a general rotation matrix. So this is the matrix elements, and then how this is actually formed from the product of two different your J1 and J2 now written in terms of the what you call JM eigenstates here. So this is the putting the identity resolution here and another identity resolution here. So you get that and this one there, and that tells us how we form the general matrix elements, okay, and that involves the Clebsch-Gordon coefficients. So similarly in this particular case, so what we have, we are supposed to think of how these spherical tensors, what you call matrix element, being transformed according to these rotation operators. So again, in this particular case, I think let me just look where the identity is supposed to come in. Why it's not moving? Yeah. So over here is your identity is C. Here's one of the identity here. Hang on. This is K1, K2, Q1, Q2, KQ. That is that. So this is another Clebsch-Gordon coefficient here. Another Clebsch-Gordon coefficient. I thought I had it. It's K1, K2, and I put a K double dash, Q dash. Okay, I just can't remember how I did it. But okay, probably most of the, I'm going to skip this proof if you don't mind. So that, no, essentially what we want is to get this idea of a spherical tensor of rank K being given in terms of the product of two tensors of rank K1 and K2, and essentially there will be some Clebsch-Gordon coefficient coming in. Okay, sorry about this, I'm not prepared for today. This, but anyway, I've forgotten about it. So, so that is more or less the behavior of how to do a tensor product between two spherical tensors. Okay. The one that we have demonstrated in a little bit more detail is the case of the spherical tensor of rank 2, which is taking product of tensor product of two Cartesian vectors. So this is much more complicated, and probably we'll be using less of this thing. Okay. Next is looking at this tensor operators matrix elements. Okay, so the tensor operators matrix elements are the ones being sandwiched here, okay, by your J and M eigenstates. Let me just see. It's like your matrix elements over here. So this is rotation matrix. Yeah, okay. So these are already in terms of the matrix elements there. Okay. TQK. I'm trying to avoid this. Okay. All right, never mind. Let me just read it what it says here. So your tensor operators, remember they are operators. So in other words, you need to form a representation of it, and usually we use the matrix representation, and the matrix representation is coming from the angular momentum eigenstates. Okay, your alpha and alpha dash here is just possibly another quantum number, just like in the case of say hydrogen atom. Then you have your principal quantum number together with orbital angular momentum. So this one is like your alpha here. Okay, so in other words, what we have in this particular case is you can see there is a kind of an addition rule for the components. Okay, so in other words, this is your beginning state. Okay, with what you call m value there, and then remember your q behaves like your m. So in other words, these two acting together over here, okay, it's like one particular state, and that state will now meet with this taken the inner product with this state which has m dash. So the only way that this two can be non-zero is that when this m dash together with this this effective state that comes from this spherical tensor acting on this particular state obeys this particular relationship. So you can see that this q sort of adds on to this m value, okay, and then when contracted with this, or no, taken the inner product with this m dash, if m dash is not equals q plus m, this thing will be equal to 0. Okay. Again, I'm trying to avoid the proof because I have not gone through this proof. You can see we can actually understand this. This one is much simpler than the one above. Okay. So that is how you get one of the way of getting the matrix element, just looking at all the zero entries first, and then the rest of the components will have to come from some angular momentum kind of what you call behavior. Okay, so next thing that we want to do is essentially, and again, I'm not going to go through the proof because I've sort of ignored this during my morning reading in a way. So again, here is essentially a much more general result saying that if you have this matrix element of EQK, okay, then you can actually bring out the part that depends on M. Here again, you can see what's happening over here. Here your M dash will meet your Q and M here, which comes in here. So this is like what you call M1, M2. Okay. And this is like your J1, J2. So you can bring that part out from this matrix element. So in other words, here you can see that this is essentially like your Clebsch-Gordon coefficient. Okay. So M1, M2 here has to be equals to this M dash. Okay. And then there will be the various different possibilities of this combination of J1 and J2 to give you Jm. Okay. J dash, sorry. Right. So what happens over here is it brings out all this M dependence into this Clebsch-Gordon coefficient, and what's left to figure out essentially the part of the tensor that depends on your other quantum numbers, in this case with respect to angular momentum is the j and j dash. You have j dash here, you have j here. So in other words, this part, okay, will not depend on your m dash, and also your component of your spherical tensor Q. Okay? So essentially, this is the Wigner-Eckart theorem, and this has been used in when studying spectra of operators. Okay, so that you are able to find out some identities and things like that. Okay, so I think I will skip this. Most of the time, this is quite difficult. Let's look at the example. So here is an example of rank 0. Okay. My cat is doing something there. Here's a tensor of rank 0. So you wouldn't expect much of tensor of rank 0 because this is a scalar operator. Okay, but just let's treat it as a tensor operator. So we can, in other words, what we can do is to apply the Wigner-Eckart theorem. So in other words, the part that depends on m0, q equals 0 here, m dash will come in this Clebsch-Gordan coefficient, and you're left with something that depends on your j and j dash. Okay. So your Clebsch-Gordan coefficient will have this value, and your part over here will be determined in another manner. So in other words, it has come from, say, some other identities which have not mentioned anything over here. Right, let's look at another one which is much more interesting. It's a vector operator, rank 1. Again, over here you can see I'm using the see what's happening. Vector operator V with components V, Q equals to plus or minus 1, 0. So these are the components here. And then we look at the case when J equals to 0. Okay, so that means here I'm taking J equals 0. When J equals 0, the only M that you can have over here is M equals 0. So then you can apply this again, the Wigner-Eckart theorem. Okay, so you have your Q and then your so-called J1, sorry, M1 here, which is 0. So I will have this Clebsch-Gordan coefficient coming here. So this is your M1, and this is M2, and this is J, and then this is the rank of the what you call tensor operator, which is 1. Okay, 0, k equals to 1. Okay, so again, what's left is this part, which is again will be obtained from a different kind of process. What is this? Okay. So over here, there is some physical implications coming from this equation, saying that here, once you start with a j equals 0, that which is we assume over here. Okay, so here you can think of your initial state, acted upon by a spherical tensor operator here. Okay, but because of this being a vector operator, meaning the part that allows you to go to a different j value will not be allowed because of this equation. Okay, so J dash has to be equals to 1, meaning because the vector operator has rank 1, somehow you can't have the transition between this state to this particular state. Okay. So these are some of the implications of Wigner-Eckart theorem. So you can actually see some kind of what sometimes I think I mentioned this before, what we call the selection rules. Okay, so certain transition is you can see that it's not allowed because of the rank of the tensor operator that comes into the picture. Some of the things that we may want to consider, for example, is when we consider a potential energy operator that depends on, say, the electric field. Sorry, I'm using two different cues here. So your V is QE, and this QE is a vector operator. So in other words, there will be certain transition because of this interaction. There will be certain transition being not allowed. Okay, and this one below is for the case of J not equal to 0. Okay, so that means I'm considering here your general J, and then of course using the Wigner-Eckart theorem again, and then you'll see that your J dash, let me see, your J dash has to be either one of the string because of J dash is going to be interacting with this vector operator which has rank 1, so either you add the rank of the vector operator to J or you subtract. Okay, and of course the rank 0. Remember that your this is just like your angular momentum addition earlier. So if you have J1, J2, then the total angular momentum can go from J1 plus J2 to modulus of J1 minus J2. Okay, so again, this tells about the possibility of what kind of transitions actually allowed in this particular matrix element. Okay. Finally, this is the case of J equals to J dash. Again, I'm not going to go through the proof because I've not looked at it properly. If you have most of the time, okay, let me just mention this is quite a difficult topic to go through. So normally I would not ask you to prove it unless it's a kind of a research assignment kind of thing. Okay? So I'll probably give you some things to do of that nature. Okay, look at certain papers where you have those proof coming in. Okay, so one of the things that we had earlier was what I've forgotten to put this on the Putra Blast is the paper that talks about spin half spherical harmonics. Okay, so again, those are a nice thing to actually, if you can go through the details, it would be nice. Okay, but you don't expect that to come out from say in your tests and exams. Okay, so similarly with this proof, I do not require you to actually to prove them in exams. Okay. So over here, there you can see what happens in this particular case. You have a vector operator again, and then your J is the same. So in other words, what happens over here is like the case. Let me just check. Is that correct? Yeah, okay, that's JJ plus 1 H bar squared. So this is like your just check down here. So okay, this is the part which is supposed to be independent of your J and of your M dash and M, and this is the part. If I'm saying this correctly. Sorry about this. Let me just look at it. So that gives you that. That is actually the. Okay, so that means this one is a bit strange. I have to properly think about this. I, I still think that this is the one that gives you the independence between your M and M dash. Okay. And then this one is just your matrix elements that you have for your. Okay, maybe I had it opposite. So this will depend on your M dash, of course. You can see that here, but here essentially the one that is independent of your M dash. Okay, let me, I think I probably want to skip the rest of this because it gets too complicated on here. These are all the proof, and that's probably the last of it. Okay. Sorry about this, but Wigner-Eckart Theorem is not a simple topic to learn, but the idea is essentially, again, you have your tensor operators to worry about when you do, say, calculations of expectation values, for example. Then you might have operators that I mentioned earlier, like your electric field operator. What was it? I mentioned that. Yeah, things like this. And this will appear in realistic calculations, and then you have to handle how this vector operators, in this particular case, would actually determine what kind of transitions are allowed and what transitions are not allowed. Okay. So I will pause for a while and ask questions if this is anything meaningful to you or not. I mean, I know it's complicated at this stage because, particularly, I'm ignoring the proofs, in, not just because I didn't prepare for it, but it's because it's too complicated for me to ask inside a particular exam. Okay, it may appear, as I said, in some kind of research reading or some assignment that might have parts of it. Okay, so these are things that you probably will have to do at some point. I've yet to do the first assignment, but let me think. Now is week 4, right? Okay, so that makes me in need of rush. So I probably think that I will skip this particular lecture for the first test. Okay, so the first test should go up to lecture. This is up to lecture 4, I guess. Lecture 4 is still your angular momentum addition. So the Wigner-Eckart thing will not appear in the first test. Okay. Any questions so far? I have to.
Doctor,
Pardon?
we need more time to absorb it. Yeah, exactly.
Yeah, I take time to go through it. It's just that I don't have usually the time. Okay. Now, one of the things that I was trying to do just before I came in was to prepare the notes for the next lecture. Okay. And I had several options for me to consider. One option is just to go direct into some kind of approximation method, and I do it differently each time. No, I teach this particular subject. I tend to see what's best for the student and what's best for me to prepare. Okay. Once I did it with the next topic will be identical particles, and I think that's it. And normally I skip this particular chapter of Sakurai, which is on symmetries. So I'm thinking probably this time around I will take symmetries to come in because it's much simpler and I can write the notes easily. Well, at least no, I think it's easy, but it still takes time. So I've started preparing this set of notes, lecture 6 over here, which I hope to sort of continue what we had previously. So these are my notes, which is still incomplete. So I still have a long way to go to do this. But probably what I'll do here is to look at Sakurai's book. Essentially, Sakurai is probably not complete in its discussion about symmetries. So if there's some thing that I think I should add in, I will add in later in the notes. But for now, let's look at this particular chapter on symmetry in quantum mechanics. Okay. So again, the idea is one can run away from comparing the case of the quantum mechanics case with the classical case. So in classical case, you also have all these symmetries coming in, and sometimes we make our analogous statements in quantum theory through this classical case. So example idea of symmetries is probably when one looks at a particular transformation, for example here. So here we are considering a kind of translations in space. Okay. And if the theory, I will tell you what the theory is supposed to mean. If the theory is actually invariant under this change of what you call variables, so to speak, so you can think of this qi plus delta qi to be equals to qi dash. So in other words, you are using a different variable with this constant addition to this variable qi. Okay, so this is essentially just a translation by a constant. Okay, so if the theory itself is not sensitive to this what I call transformation, then we say that it is symmetric with respect to this transformation. Okay, So how do you determine the theory to be symmetric? Is normally we look at equations like this. Okay, so in other words, over here you have L, Q, say I, and then QI dot. This is the Lagrangian. You're supposed to know this in classical mechanics. And then if under this transformation, so you transform to say QI dash Q dot I dash, okay, and then T. Let's keep T unchanged at the moment. Then if this thing doesn't change its equation, for example, then essentially that tells us your partial L partial Qi equals 0. Okay, under this, well, if you really think what this is, under first order, this would be equals to LQI QI dot T plus partial L partial QI delta QI. There's supposed to be more terms here, but no, let's just consider this. So if it's unchanged, in other words, this one equals to that, or this one equals to that, okay, that means your partial L partial Qi has to be equal to 0. Okay, and because of that, you use your Euler-Lagrange equation. So partial L partial Qi is 0, so I don't have that anymore. So I will only have d dt of partial L partial Qi dot. But what is partial L partial Qi dot? That is essentially your momenta. Okay, so in other words, what we have from that equation, we will have d dt pi equals 0. Or in other words, this is another way of saying your momenta is conserved. Okay, so you have this idea about a theory being invariant will lead to some kind of conservation law. There's a general theorem about this, which is called Noether's theorem. But I will not go through the details of this. This is much more general. Okay, but essentially you have this kind of thing appearing inside a particular theory. So if things doesn't change under certain transformation, then you'll find that okay, there will be some conservation laws or some constant motion. So this is in terms of Lagrangian. You can do the same in terms of Hamiltonian. So I can talk about H, Q, I, P, I, T transform to H, Q, I dash Pi dash T, and if again you can relate this with the original one. So this is HQI Pi T plus partial H partial Qi delta Qi, and then some other things. Okay, so if the theory is unchanged under this translation that we had earlier, okay, this one, okay, then your partial H partial Qi should be equal to 0. Then by virtue of your Hamilton's equation, partial H partial Qi equals to d dt of Pi. Not sure whether there's a minus sign. I think there's a minus sign. Okay. So if you have this to be 0, that means you get back to the same conclusion that your momenta is conserved. Okay. But more than that, there are other things when it comes to quantum mechanics. You talk about degeneracies. Okay, so let me see over here. Why is it jumping straight into that. There's a missing page. 262, yeah, 265. So so there's a missing page. Oh dear. So maybe I have to go back to this notes then. So the other thing besides having conservation laws, there is also what we call degeneracies that one has to think about. Okay, so let me just do this. I'm just following Sakura at this stage. So I have to get another copy of that book electronically. So here is a symmetry operation. Okay, symmetry operation. So in quantum mechanics, this is implemented by unitary operators. Okay, so your symmetry operation is now given by a unitary operator S hat. So it's an operator. Okay, but I can now consider the case of the infinitesimal case. So usually, maybe I go to the whiteboard in this case. So usually a unitary operator are given in terms of exponential minus I, G, then what's the, just to check to be consistent, epsilon, okay. So there will be a parameter epsilon here. So these are usually the normal form that we will have for the case of a unitary operator. And your epsilon here is what we call the transformation parameter. And then your G is what we call the generator of transformation. Oops. Never mind. Okay, so this generator of transformation, in order to make this a unitary operator, your G has to be Hermitian. Okay, then this thing will be unitary. One could consider your generator to be a non-Hermitian operator. So these are things sometimes different authors might actually do this kind of tricks in order to confuse everyone. So what they do, instead of writing this in terms of this exponential here, they will just simply write exponential G epsilon OH. Then in this particular case, your G will not be Hermitian. Okay, so in fact, there are various ways of doing this. But no, man, we are not interested in those. Oops. Okay, so back to the notes. So once you have that, then you apply this to your operators. Okay, particularly a physical system. Normally, one considers a Hamiltonian. Okay, so if just like your Hamiltonian that you use for your Lagrange, your Hamiltonian mechanics before, okay, in quantum mechanics, then you consider your Hamiltonian operator, okay, and in this particular case, you want it to have this idea of the Hamiltonian is not going to change under the symmetry transformation. So this is just like your, you go here, U dagger O U. So this is how an operator transform. Okay. So if this transformation is invariant under this, if this operator is invariant under the transformation, then this becomes O. So here, place this by H, and you get your U dagger H U equals to H. Okay. So in this context, this is one has to be careful. Sometimes the word symmetry has been used in different contexts, but this is sometimes called symmetry transformation. Okay, the symmetry transformation here is symmetry with respect to the Hamiltonian. Okay, the Hamiltonian that represents the energy. Okay, so in this particular case, what happens then? If you plug in your S here, which is your U in my previous scribble, okay, plug S as this infinitesimal version of this into here, and then you expand out, then you'll be able to get it in terms of a commutator with this generator here with the Hamiltonian. Okay, and if you have this, okay, coming from there, then from the Heisenberg equation of motion, I think, if I'm not mistaken, I have to check this because I can get the equations wrong sometimes because of the sign. This is just for me to check. I never memorize any equation usually. Heisenberg equation of motion. Just to make sure whether it's I over H. Okay. So essentially what one needs is your operator, and I'm assuming that the operator doesn't have a time explicit time dependence, so I don't have that extra factor from the equation of Wikipedia. So I will just have I over H bar which way around, or H first, okay. So H O. But if you have a symmetric transformation, then this commutator is going to be 0. That means this observable, okay, this operator will not change with respect to time. And then this is what we call constants of motion. Okay. So that generator, in the case of a space translation, okay, that generator is given by the momentum operator. So that's how you get the relationship with the classical case and the quantum case. You have more or less the same idea. Okay, your momenta is a generator of space translations in classical case as well as in the quantum case. And in those cases where it's actually representing a symmetric transformation for which your Hamiltonian doesn't change, then it will be a constant of motion. So the other thing is this idea of degeneracy. Okay, so let's suppose this G, which generates the symmetry transformation, meaning it commutes with H, okay, has an eigenstate at some time t naught, an initial time t naught, labeled by this G dash, which is your eigenvalue. Then, according to your time evolution equation for the states, it's given by a unitary operator here, which is an evolution operator here. It will change from G dash T naught to G dash T, okay? Then, because of the that G commutes with H, then it should also commute with U. So I can do this, for example, G acting on U T T naught G dash T, G dash T, sorry, G dash T naught, sorry. But now I can interchange this because it commutes. So I have this to be equals to U T T naught D times G dash T naught. Or in other words, this will give you G dash, it's just a value because it's an eigenvalue of your operator G, and your U T T naught will multiply with your G dash T naught to give you G dash T. So in other words, G dash T will have the same eigenvalue as G dash T naught. Okay, so in other words, if your G dash T and G dash T naught are really two different physical states, meaning they are not equal, even considering the phase factor. So remember that, let me go here, a state psi, if we multiply by a phase factor here, this is actually representing the same state, because when you do inner product, say psi dash psi, then you find that this phase, so this is E minus I theta, EI theta, psi, so you get back the same inner product. Okay, sorry, this should be an error. Okay, so in other words, modulo this multiplication, if psi dash and if let me go back, if your G dash T is a totally different physical state than G dash T naught, then you have G dash T having the same eigenvalue as G dash T naught. So in other words, the eigenvalue G dash is said to be degenerate. Okay, that doesn't count if it's just the difference is just a modulo phase factor. Okay, so one has to be careful about that. So in the same way, one can talk about innate energy degeneracies. But I think I've exhausted the time, so I will continue with this perhaps in the next lecture on Thursday. Okay, so I'll stop there for today. So sorry about the parts which I do not go through in detail. So let me just get the attendance list. So at this stage, I'm still planning which direction I need to go, because I could now easily go from symmetries to many particle states, because many particle states are talking about permutation symmetries. So in that way, there's a continuity there, but most of the book seems to put identical particles right at the end of the book. So that's, I have to think carefully, whether which is better. Okay, so I'll stop there for today. Thank you, everyone.
Thank you, Doctor.
Okay, bye.